Welcome to Online Precalculus. Today, we are going to cover section 4.8, Applications of Trigonometric Functions. Our objectives for this section are to solve a right triangle, to solve problems involving bearings and nautical measures, and finally to model simple harmonic motion. All right, so the first thing we're going to talk about is solving a right triangle. Yeah. So to solve a right triangle, it means that we're going to find all the missing lengths of its side and all the measurement of its angles. So we're basically going to find all three sides and all three angles. And we already know one angle. We already know the right angle, okay? But we're going to go and get all the other ones. A note on our notation. If you notice that angle A is right there, okay? Side A is the side across from that angle. Side C is always going to be our right angle, and angle C is always going to be our right angle, and side C will always be our hypotenuse. And you can see that B is across from B. Angles are labeled with capital letters, and sides are labeled with lowercase letters. So let's start with this triangle. Okay, around the lengths of 2 decimal places. So when we first look at a triangle, we have to decide what is the best way to solve for everything. So we need all three angles. We have angle A, angle B, and angle C, and side A, side B, and side C. Right? Solving a right triangle means solving every single angle. Well, angle A was 34.5 degrees, and angle C is 90. And then to find the other angle, angle B, we can use our triangle angle sum theorem that says that every single angle in a triangle has to add up to 180 degrees. So angle B is going to be 55.5 degrees because 90 plus 34 plus 55.5 is equal to 180. Okay. Now I have side B. So side B is 10.5. Okay, so now I just need one of the other two. We have a couple of approaches here. Let's get side A first. If I look at side A, I notice that, well, I know how big angle B is, but angle A I'm given. All right, so let's start with angle A. So if we remember, the trig ratios of a right triangle can be remembered with the acronym SOHCAHTOA. Sine is the opposite over the hypotenuse, cosine is the adjacent over the hypotenuse, and tangent is the opposite over the adjacent. So if I start with this angle, I want to know the opposite side, I know the adjacent side. So that is opposite and adjacent is the tangent ratio. So I can say that the tangent of 34.5 is going to be equal to something over 10.5. The opposite over the adjacent. All I need now is a calculator set up in degrees because we are going to use degrees in most of this section as opposed to radians, which we used a lot previously. Just multiply both sides by 10.5. So 10.5 times the tangent of 34.5 gives me 7.22. Okay, so that is side A. Okay, so now I could use either the Pythagorean theorem, because I know two sides of a right triangle, or another trig ratio. I'm just going to use another trig ratio because I have a nice easy one right here. If I want the hypotenuse, I could say that the cosine of 34.5 is equal to the adjacent over the hypotenuse. So the adjacent, 10.5, right? That's the angle next to, or the side next to the angle A, over C. multiply both sides by c, and divide out the cosine of 34.5, and we get that c is equal to 10.5 divided by the cosine of 34.5, which is 12.74. Okay, let's double check and make sure my answers make sense. A is the smallest angle, A is the smallest side, B is in the middle, C is the largest side, the hypotenuse, and it should be. All my answers make sense, and I have now solved the right triangle because I've gotten every side and every angle. I don't think I put a God. No, I didn't put the God problem down here. All right, so trigonometry was first developed for measuring heights and distances that were inconvenient or impossible to measure directly, right? Using triangles, using trigonometry. So when we solve application problems, the first thing we want to do is we're going to need to draw a picture. Okay. You might be looking up, you might be looking down. It depends on what the question says. So you just got to be careful that you are drawing the picture the right way, or drawing the function the right way. From a point on level ground, 125 feet from the base of the tower, the angle of elevation means you're looking up is 57.2 degrees. So here's a representation of that. So 125 feet away from the tower, you're looking up at the top of the tower at 57.2 degrees. So kind of hard to go up and climb up and measure this tower. Easier to measure a point on the ground and an angle as you are looking up. What do I want to know? I want to know that. I know that. I know this angle. That is the opposite and adjacent. So that is the tangent of 57.2 is equal to the opposite over the adjacent. Okay. And I expect, if this is 57 and this is 90, that means this angle was a little bit smaller. I expect this to be this angle smaller, so this angle is bigger. I expect A to be a little bit bigger than 125. Let's try it. Multiply both sides by 125, and we get that A is about 194. So 57.2. Whoops. 125 times tangent of 57.2 gives me 193.9. So 193.9. And nearest foot, so it was 194. Okay. The next example, example 3, illustrates how to find the measure of an acute angle of a right triangle if the lengths of two sides are known. So now what we're going to have to do is we're going to have to find an angle. Okay, so a kite flies at 30 feet when 65 feet is out. So when you ride a kite, right, when you fly a kite, you're letting out the string. Okay, so that's the distance right there, 65 feet, and it's 30 feet off the ground. If the string is in a straight line, find the angle that it makes with the ground. So this is what I'm looking for. All right, so what do you know? I know the opposite side. I know the hypotenuse, SOHCAHTOA. So that would be that the sine of theta is equal to the opposite over the hypotenuse, which means that I'm going to have to get theta by itself. So we are looking for the inverse sine, right? That's what inverse sine does. It tells you what angle gives you, what angle has a sine of 30 over 65. So remember that inverse sine is probably in the upper buttons, like the shift function, and we just go 30 over 65, and we get my answer that theta is going to be 27 point, round to the nearest tenth, 27.5 degrees. Okay. So altogether, it's not too bad when we have to solve for, right, when we have to either solve a triangle or solve for one thing specifically. This next problem has two triangles inside of it. So, and we'll look at the picture in a second, but see if you can visualize this picture before I actually show you. You are taking your first hot air balloon ride. Your friend is standing on level ground, 100 feet away from your point of launch, making a video of the terrified look on your rapidly ascending face. How rapidly? At one instant, the angle of elevation from the video camera to your face is 31.7. 1 minute later, it is 76.2. How far did you travel during that minute? So if you can imagine this, the balloon is here going up. Your friend is here. First, you have a small angle of elevation, then a much bigger one. Okay, and here is a much better picture of that. Okay, so there's our picture. So what do we want to know? We want to know how far he went in the minute. So basically, we want to know that distance right there from the first point on the balloon to the second point on the balloon. Okay. How far did you travel to the nearest foot during that 1 minute? Okay, so in order to do that, we're going to need A, we're going to need B, and we're just going to need to subtract them. Well, the small triangle right down here, I want the opposite side. I know the adjacent side, so I can say that the tangent of 31.7 is going to be A over 100. So that is, so A is going to be 61.8. And then the tangent, oops, the tangent, right? I now know this big angle, 76. I want to know that side. The tangent of 76.2 degrees is going to be B over 100. So that makes B 407. Okay. And then to get my answer, right, I just take B minus A. So that's 407.1 minus 61.8 to give me a total distance traveled of 345 feet, 0.3 during that 1 minute of travel. Okay, so we can do a lot of there's a lot of situations with drawing triangles and solving for various sides or various angles. The key to this is if you don't have the picture to be able to draw an accurate representation of what is going on in the problem. Okay, next, trigonometry and bearings. So in navigation and surveying problems, the term bearing is used to specify the location of one point relative to another, the direction you're going. We might have seen, might be a little bit more familiar with a compass and saying that you're going a certain number of degrees on the compass. Bearings are a little bit different. So the bearing from point O to point P is always an acute angle, always measured in degrees, and it's the distance between wherever you're going, the ray of the direction you're going, and the north-south line. Here's the way it works. So this point right here, you always start with north or south. So are you going north or south? You're going north 40 degrees to the east. So you start with the north-south line, and then you say how far are you going, east or west. So this bearing right here would be north, because you're going north, and west. So north, 65 degrees to the west. This one is, right, down here. So it's south, 70 degrees towards the east. Okay, so each bearing, here's a little breakdown. Each bearing has three parts, north or south, the acute angle, and then east or west. Okay? If you're on the north side of the north-south line, you write north first. The acute angle is measured from the south side, you write south first. Then you go from the angle, and then you say whether you're going east or west. Okay? So, the bearing from O to B. There's B. O is always going to be the center. So that's north, 40 degrees west. Okay? North, then west. Okay? From O to A. It's a little trickier. North, it's not 20, it's this angle from the north-south line. So that's 70 degrees east. How do I know it's 70? Because this is 90 degrees, right? Each quadrant is 90 degrees. I think I put it, no, I didn't put, well, let's just do this one anyway. I didn't put the regular problems here. O to B, well, that's a good one. It's north, so that's out. It's going to be west, so I can always eliminate this, and then that angle is 46. So the answer would be C. Okay. Let's see how we can use this in a problem. So, boat leaves the entrance to a harbor and travels 25 miles on a bearing of north 42 degrees east. So we're starting here, and we're going that direction. Then the captain turns 90 degrees and travels 18 miles on a bearing of south 48 degrees east until you get there. The question is, how far is the boat from the harbor entrance? So what is C? All right, well, what do we know? We know this side, we know this side. We do know two sides of a right triangle. So to find C, the distance to the harbor entrance, we can always use the Pythagorean theorem, which says that C squared is equal to A squared plus B squared. Okay, so that means, let's move this if I can. Move this out of the way for a second. Okay, so that means that C squared is equal to 25 squared plus 18 squared, which is 949. Right. Yep. And then we just take the square root of that, and we get that C is 30.8 miles. Okay. Now we just need the bearing. Okay. So the bearing of the boat from the harbor entrance. So we want the bearing of, we basically need theta right here. We want this bearing right from there to there. So it's going to be north, it's going to be east, and then we just need this angle right here that we can add to this one. All right, let's analyze this. Opposite, adjacent. I have the hypotenuse, it's right there, but I'm given the opposite and the adjacent. So use the two things that you know for sure are right. That's right, but just in case, let's be careful. And let's say that the tangent of theta, opposite over adjacent, is 18 over 25. Opposite, adjacent. So that means that theta is equal to, whoops, the inverse tangent of 18 over 25. Okay, pop that in my calculator. Over 25, and I get 35.8 degrees. Okay, that's not the answer because that's theta, right? The bearing is this whole angle from the north-south line, so that means we have to add back that 42. So the answer would be north, add 42 to my 35.8, and we get 77.8 degrees east. And that is my bearing from the harbor to the boat. Okay. Let's talk a little bit about simple harmonic motion. So because of the periodic nature of sines and cosines, right? The fact that it, keeps repeating, they can be used to model phenomena that occur again and again, like vibratory or oscillatory motion, such as guitar strings, right? Pluck it, it's going to keep vibrating. It's eventually going to stop, but we can assume that it's going to go on at the same amplitude for forever. The swinging of a pendulum, bobbing of an object to a spring, and trigonometric functions are also used to describe radio waves from your favorite FM station. FM stands for frequency modulated. That means we're just going to change the frequency to get to different radio stations. AM means amplitude modulated. So with the frequency, we're going to change the period of my function. For AM radio stations, we just change the power. We change the height of the carrier wave, right? And your radio is able to tune into them if anybody used a radio anymore. Okay. So to see how all trigonometric functions are used to model vibratory motion, consider this. So think about it. A ball is attached to a spring and hung from the ceiling. You pull the ball down and then let it go. If you don't worry about friction and air resistance, the ball will keep going up and down, something like this. So you pull the spring, right? This is rest position, right? Here's the midline. You pull it down, you let it go. It goes up and then goes back down and back up and then back down over a course of however long. Okay. So we use d-axis where d represents distance. On the axis, the position of the ball before you pull it down is 0. This is rest position, equilibrium position, whatever you want to use for that. So you're going to pull the ball down to -4. So just an easy way to keep track of what the middle is. So we're pulling it down 4, releasing it, and it's going to go down 4 and up 4 with this simple harmonic motion picture. Okay. So with simple harmonic motion, don't get too crazy here, right? The distance from an origin is given either with a cosine or a sine function. This one, I would have used a cosine function, inverted, right, reflected, because it started at a minimum. If it started at 0, you would use a sine function, okay? But you can use either one. You just have to phase shift a sine function. Right? The motion has an amplitude absolute value of a. The maximum displacement from the rest position. The period is 2 pi over omega, where omega is greater than 0, and it's time it takes for the motion to go through one cycle. Same as how we graphed the period of a function was 2 pi over b. Just here, we just have a different letter to represent something different. Okay. In describing this harmonic motion, the equation with the cosine function is used if the object is at its greatest distance from its rest position when time is 0. And then use sine if it starts at its rest position. Okay, so I did mention that. All right, so again, a ball on a string is pulled 4 inches below its rest position and then released. You're starting at somewhere far from the rest position, or not the rest position. So we're going to use cosine. The period is 6 seconds. Write the equation. Well, first, my displacement is going to be 4, but because I am moving this down, okay, normally cosine starts at a maximum. right? I'm going to start it below. You can pull the ball up and let it go, but we didn't. We pulled it down. So I'm going to start at the bottom. So I'm just going to invert. I'm going to reflect the cosine function. All right. So we need some sort of period change here, right? And a variable, either x or not x. You know, time would be our variable, right? Because we're talking about seconds. All right, what's the period? The period is going to be 2 pi over omega or b, whatever you want to use. My period is 6 seconds. Oops. So 2 pi over omega. So omega would be 2 pi over 6, which is pi over 3. Okay, so as long as you remember exactly how the transformations of a sine and cosine function work, writing the equation is not hard if you're given all this information. Okay, so you know the period. If you have a time for the period, you know you want to use the cosine function. Just plug it back in. We'll finish with something called frequency. Frequency is just the inverse of period. Okay, so the periodic harmonic motion in the last question was 6 seconds. It takes 6 seconds for the moving object to complete one cycle. Thus, 1/6 of a cycle is completed every second, and we call that the frequency. And it decides the number of cycles per unit time, seconds, minutes, whatever. Okay, so the frequency is just the opposite of the period, because the period was 2 pi over omega, and the frequency would just be 1 over the period, omega over 2 pi. Okay, so here we go. So here's here's a block on a smooth surface attached with a spring. The mass moves in a simple harmonic motion modeled with this equation. Notice that we're going to start by pulling it this way, so that way it's going to start positive. We could push it to -10 and let it go, but then that would be an equation like that. Okay, what is the maximum displacement? How much did this thing move? So A would be, so the answer for A is 10. Okay? Because you're going to pull it to 10, so the maximum displacement is the amplitude. Right? It does travel 20 units, right? But the maximum displacement is 10 and then -10. So B is the frequency. So the frequency is 1 over the period, or omega over 2 pi. So that's going to be, that's omega, pi over 6 over 2 pi. So we just multiply by the reciprocals, and we get 1/12. So that means that this goes through a 1/12 of an oscillation per unit of time, and the time measured to a t, measured in seconds. Okay, so the period, you can do the whole calculation again if you want, but it's just the reciprocal of frequency. So let's see, 12 seconds. Okay, so the time required for one complete cycle would be 12 seconds. All right, and that was 4.8, applications of trigonometric functions.